So in this related rates problem, we read that air pressure, P, depends on altitude, Z, by the following function. Okay, so pressure is equal to some initial pressure times E to the negative mgz over kt, where P naught, okay, m, g, k, and t are all considered constants. So a lot of that stuff would have just been measured. Okay, so let's kind of zoom in on that. This equation right here, these guys here would have all been measured. M, when I looked this up, M is the mass of air molecules, G is your gravitational constant, K is a constant based on the air, T is going to be temperature, P would be some measured pressure, because what we're looking at here is how, when given these conditions, when I change my altitude, how does pressure change? That's what we're looking for. So what do we know? Well, we know the equation. P is equal to P naught E to the negative mgz over kt. Okay. What I know that most of these guys are constants here. What I'm looking for here is, what I want is how fast pressure is changing. So I want dP by dt. I know that we're looking at the specific spot when the altitude is 3 kilometers. And I know that the altitude is changing, so dz by dt is decreasing at a rate of 50 meters per second. Okay, now probably want to keep this in terms of meters. So this is going to be 50 meters per second, but then that means I got to go up here and change this 3 kilometers to 3,000 meters, because I want to make sure that I'm in the right units here. Now, once that's all kind of established, let's just go to our equation. So P is equal to P naught E to the negative mgz over kt. Okay, now take the derivative, dP by dt is going to equal, okay, now in this case right here, we're assuming constant, 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 constant. And I know in some cases it's maybe even a little bit unnatural to think of T, particularly the temperature, being a constant as altitude changes, but we're just changing in a fairly local area here. This was the way this equation was being applied here. So the derivative of this is going to be P naught E to the negative mgz over kt. Then we're going to multiply by the derivative of the exponent, which would be negative mg over kt times dz by dt, because of how that changes in time. And so now we're just going to plug this in, and there's not a whole lot for us to do. This was more about just practicing or reminding us how to take the derivative of an exponential. So this is going to be negative mg over kt, those are constants, I don't know what they are, times P naught, and then this is going to be E to the negative mg, well, Z I do know. Okay, so, sorry, those are just a little interruption there. So those are constants here, but I do know what Z is. Z is 3,000 here. So I can write that in here. So this will be times 3,000 over kt, don't know what those are. And I know that this is going to be negative 50 meters per second. So just putting that all together, notice that those negatives are going to cancel, so this is going to be 50 mg over kt times the initial pressure E to the negative, and we might as well just plug that in, 3,000 mg over kt. That's about the best that I can do.